All right, so for case 4, our final case for partial fraction decompositions, we've already looked at what happens if you have a distinct linear factor, what happens if you have repeated linear factors, and what happens if you have a distinct irreducible quadratic factor. Well, now the question is, what happens when you have a repeated irreducible quadratic factor? Okay? And the concept here is almost identical to what we saw in the previous cases. So if we have a factor that is irreducible and it's a quadratic and it's repeated r times, then the partial fraction decomposition will give us something that looks like this. So we have a1x plus b1 over ax squared plus bx plus c plus a2x plus b2 over ax squared plus bx plus c squared, plus etc., all the way up to the r term. So arx plus br over ax squared plus bx plus c to the r power. So same idea as with repeated linear factors, where you just are basically counting up. So you get the first power, second power, third, fourth, etc., up to the rth power, whatever that may be. Okay? The only difference, of course, is that because they're quadratic, we have to take the ax plus b in the numerator. Okay? So first off, before we do a full integration example, because these can get pretty unruly when you're dealing with lots of different factors in the denominator, particularly repeated. So we're going to look at this example, and it says write out the form of the partial fraction decomposition of this function. So don't solve an integral, but just write out the partial fraction decomps. So we've got x cubed plus x squared plus 1 over x times x minus 1 times x squared plus x plus 1 times x squared plus 1 cubed. So let's identify what we have here. I have a distinct linear factor, a distinct linear factor, a distinct quadratic factor that is not reducible, and repeated quadratic factors. Okay, so I've got those that we're going to need to incorporate here. So let's give this a try. So we have a over x plus b over x minus 1. Okay, so those are our single linear factors, plus cx plus d, I'm just kind of counting up through the alphabet here, over the first quadratic factor, so x squared plus x plus 1, it's non-repeated. Now we get to all the repeated ones. So we have ex plus f over x squared plus 1, right, to the first power, plus gx plus h over x squared plus 1 squared, plus ix plus j over x squared plus 1 cubed. And that would be our partial fraction decomposition for this one, because it has, right, 1, 2, 3, 4, 5, 6 there. So we're going to have 6 terms in this decomposition. So integrating something like this, could be pretty darn messy, and not to even mention solving for all of those variables or those constants that we need. So that's why this one was just a setup, but we're not going to solve it. So instead, let's look at this example down here. So evaluate the integral where we have the denominator is x times x squared plus 1 squared. So that's a sum of squares, not a difference of squares. So it's irreducible quadratic, and it is repeated. Okay, so our partial fraction decomposition, let's write it over here. So partial fraction decomposition. Oops. So this is going to be 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 quantity squared. So we have the lone linear factor. Now we get the repeated factors. So we have bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 squared. Okay, and then we're going to multiply by the LCD to solve. So we get 1 minus x plus 2x squared minus x cubed equals a times x squared plus 1 squared plus bx plus c times x squared plus 1, and I'm running out of space, plus dx plus e times x. Okay, and then if you go through, right, multiply that out, distribute those to these, distribute that. So a little bit of algebra kind of grunt work there. But if we do that and then regroup based on power, we'll see that we get a plus b times x to the fourth plus cx cubed plus 2a plus b plus d x squared plus c plus e times x plus a is the only one with a constant term there. Okay, so we've got this equal to this. And now we do our next step, which of course is to equate the coefficients. Okay, so you got to be a little careful because this one is in ascending order, this one is in descending order. So just make sure you don't get them all switched around. But let's start with this one. So the fourth power, this one doesn't have a fourth power, so the coefficient must be 0. So we've got a plus b equals 0. Cx cubed, that's negative 1 x cubed, so we get c is negative 1. Then for the x squared term, we get 2a plus b plus d is 2. For the x term, we get c plus e equals negative 1. And for the constant term, we get a is 1. Okay, so a couple of these values are already given to us here. Right? We're given a and c, basically. And we just need to find b, d, and e using those values. So we can do that. I'll just kind of cut to the chase here. So we get a is 1, b is negative 1, c is negative 1, d is 1, and e is 0. Okay, so that's what we get for our values. So all those values are going to go into the partial fraction decomposition here so that we can split this ugly function into 3 smaller, more manageable functions. Okay, so let me change my color here and set up this integral. So we've got the integral of 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 quantity squared dx. Now that gets split up into 1 over x minus x plus 1 over x squared plus 1 plus x over x squared plus 1 squared dx. Okay. So we're going to then split this into 3 separate integrals, and this middle one here I can split into 2 as well. Again, I'm going to take the x over x squared minus 1, or plus 1, and I'm going to take the 1 over the x squared plus 1. So splitting that one into 2 separate integrals itself to make them easier to integrate. So this is going to give us integral 1 over x dx minus, and this minus applies to the whole thing, integral x over x squared plus 1 dx minus 1 over x squared plus 1 dx, and then plus integral of x over x squared plus 1 squared dx. And then this brings us to a point where we can integrate it. So for the integration on this one and this one are both going to be done using u substitutions. Okay, so you can do those using Calc 1 techniques. This one is that inverse tangent formula we saw earlier, and then this one is just a standard natural log. So we get ln of absolute value of x minus 1/2 of 1/2 times ln of x squared plus 1 minus inverse tangent of x minus 1 over 2 times x squared plus 1, and then plus arbitrary constant k. Again, I'm using k to not confuse it with the c that we saw. The c that we saw earlier up here. So just an arbitrary constant there. And that brings us to the end of section 7.4. So a bit of a longer one here with these 4 different cases. Just looking at all the different possible scenarios you could see popping up in these rational integrals where we need to use partial fractions to solve them. So great job making it through the end of 7.4. When we